Okay, here's the next. From counting techniques, we go to permutations. The important thing about permutations is that order is important. So we'll look at a few examples and we'll keep it hopefully fairly simple to start with. So remember, permutations, order is important. So example one, suppose there are 5 people in the race and we've got Adam, Bruce, Cameron, Dave and Ed. In how many different ways can they finish first, second and third? And we're going to list them all, and that's why we start with a nice small amount. So let's just look at Adam winning and Bruce coming second. So if Adam comes first and Bruce comes second, the only way is that Cameron comes third, Dave comes third, or Ed comes third. And that's all the different ways where Adam wins and Bruce comes second. Then we can look at when Adam wins and Cameron comes second. And obviously, if Adam and Cameron have already come first and second, third must be Bruce, Dave, or Ed. Then we can look at Adam coming first and Dave coming second. So Adam, Dave, Bruce, Adam, Dave, Cameron, Adam, Dave, Ed. Then we can look at Adam coming first and Ed coming second. So then you've got Adam and Ed, Bruce, Adam and Ed, Cameron, and Adam and Ed, Dave. And that is all the ones where Adam comes first. And already we've got 12. And then we could move on to Bruce winning and Adam coming second. So Bruce first, Adam, then Cameron, Bruce, Adam, Dave, Bruce, Adam, Ed, and Bruce, Cameron. And then you'd have 3 there as well. Then Bruce and Dave, Bruce first, Dave second, and you have 3. So you could list them all, but even just Adam coming first, there are 12 different ones. So one would assume that Bruce coming first, you'd have 12 different ones. Cameron coming first, there'd be 12 different ones. Dave, there'd be 12, and Ed, there'd be 12. So 5 times 12 is 60. So even with only 5 people, it can become very tiresome very, very quickly. So we need a rule. And again, it's like the number plate example. How many different people can finish first? 5. So once someone has finished first, how many people can finish second? 4. And once first and second are finished, how many people can come third? 3. So really, how did we get 60? 5 times 4 times 3. Suppose there are 10 people in a race. In how many ways can they finish first, second, and third? We could use the same sort of system. How many people can finish first? 10. Once first is sorted, how many people can finish second? 9. Then how many people can finish third? 8. The total number of ways this can happen is 10 times 9 times 7, which is 720. So let's start looking at taking this a bit more theoretical with a few more examples to start with. 20 horses in the Melbourne Cup. Let's suppose they all have about the same chance of winning. A bookmaker is willing to pay you $5,000 if you can pick the first 4 horses in order. Should you take that bet? Well, let's look at how many different ways the first 4 horses can finish in the Melbourne Cup. The first horse, there are 20 different horses that can finish first, then 19 different horses that can finish second, 18 different horses third, and 17 fourth. Therefore, there are 20 times 19 times 18 times 17 different ways this can happen, or 116,280 different ways. So it's probably not a really good bet. You should be getting somewhere about $100,000 for this bet. So in the first example, we were picking 3 people from 10. Order was important, so it was 10 times 9 times 8. 4 horses becomes, out of 20, becomes 20 times 19 times 18 times 17. In mathematics, we are looking for rules. There's a nice simple pattern here. If we were selecting 2 people from 10, it would be 10 times 9. If we were selecting 2 people from 20, 20 times 19. If we were selecting 4 people from 12, 12 times 11 times 10 times 9. It's a nice simple pattern. So in how many ways can first, second, and third finish if there are n people in the race? So now we're getting into algebra. If there are n people in the race, how many people can come first? N different people. Once that one person has finished first, there are n minus 1 people that could finish second, and there are n minus 2 people that could finish third, or n multiplied by n minus 1 multiplied by n minus 2. So how do we transform this to 10p3? This is something that Alan did in the lecture. He wrote this as 10p3. So 10p3 equals 10 times 9 times 8. Or even worse, he wrote NPR equals n factorial over n minus r factorial. How did he come up with this rule? So a few little quick definitions. N factorial, not sure if you've seen that before, some of you. N factorial, or 5 factorial, is just 5 times 4 times 3 times 2 times 1. 8 factorial is 8 times 7 times 6, 5, 4, 3, 2, 1. So 10 factorial is 10 times 9 times 8 times 7 times 6, all the way down to times 1. And 10 minus 3 factorial, remember, that's what the rule looks like. 10p3 is 10 factorial over 10 minus 3 factorial. So 10 minus 3 factorial is 7 factorial, which is 7 times 6 times right down to 1. Now, if we write 10 factorial over 7 factorial as a fraction, all of these things can cancel out. The 7 can cancel out with the 7, the 6 with the 6, the 5 with the 5. And all we are left with is 10 times 9 times 8. So if we have 8p5, that is just 8 factorial over 8 minus 5 is 3 factorial. So 8 times 7 times 6 all the way down to 1 divided by 3 times 2 times 1. This can cancel out. The 3 times 2 times 1 is 6. The 3 times 2 times 1 is 6. So that can cancel out and just leave us with 8 times 7 times 6 times 5 times 4. 9p2 is 9 factorial over 9 minus 2 factorial. So 9 factorial over 7 factorial. And again, I've written them out in longhand. And all this 7 times 6 times 5 times 4 can cancel out with all of that on the top, just to leave the 9 times 8. Hopefully that explains that factorial notation that Alan was using in the lecture. Thanks.